Let's look at number 6. In number 6, we're trying to figure out the units for the rate constant. So you remember that in the rate constant, K, it can have a variety of units. Equilibrium constants don't have units, but rate constants always do, and they can have a variety of units. The other thing to remember is this invert unit notation. When they say molarity minus 2, what they mean is molarity is on the bottom of the fraction, so it would just be molarity squared on the bottom. Alright, so how do we do this? Well, really all we're going to do is we're going to substitute in the units and rearrange the equation and see what cancels. So here's the general rate law. Rate is something that happens per time, like miles per hour, that kind of thing. In chemistry, you might wonder, well, what's happening in that amount of time? And I'm going to do seconds here since they seem to have seconds, but it could be hours. And it's how much molarity disappears. So our rate is molarity per second. There's our rate constant K. We know that this is units of concentration, and this guy is going to be units of concentration squared. Now all we have to do is solve for K. So I'm going to divide both sides by molarity and molarity squared so that they cancel over here. And so I will get on the other side, I still haven't changed my molarity per second, but now I have a molarity and a molarity squared down here. This molarity cancels one of these three down here on bottom, and if I do a little neatening up, I'm going to have nothing on top, so I'm going to put a 1 there, and that's what's going to be left. So my answer looks like C. Number 7. So in number 7, let's see, they have a multi-step reaction. They want to know which of these species is an intermediate. Remember, intermediates are called intermediates because they are not there in the beginning, right? Intermediate means middle. So, so you look at C and D, both got formed as the reaction went on. So there are sort of our candidates. And C gets consumed again. So D is just a product because it doesn't get consumed again. The definition of an intermediate is it has to be formed in the reaction and consumed as the reaction goes on. So the answer is C. To understand number 8, I've drawn the reaction over here. And so, oh, I keep messing this up. Alright, so I think I've solved my tablet problems. So number 8 is talking about the rate of disappearance of one chemical versus another. And so here's the idea, is remember that if we draw out the reaction and we think about what's going to happen as far as stoichiometry goes, well, it really doesn't matter what the initial concentrations are. They may be 0 for the products, but it doesn't matter. The one thing we know is this is going to be consumed at 2x, this is going to be formed at 2x, and this is going to be formed at 1x. So if we're talking about relative concentrations, 2 of these will disappear for every 2 that form. So the rate of change of NO and NOCl should be the same. And chlorine will be formed at half the rate that this one is formed and half the rate that the initial one is consumed. So that's the idea. It's based on stoichiometry. So let's see. We're looking for NO appears at twice the rate of NOCl. So we're comparing NO and NOCl. Nope, we think those two are going to be the same. NO appears at the same rate as NOCl. That looks good, so B's looking great as long as the language is right. Is NO appearing? Yes, it is. And NO3 is disappearing. So I think B is going to be the correct answer. Yep, B is going to be the correct answer. The one thing I want to say to remind you before we go on that this brings up kind of conceptually is how you would write this. So one thing I want to remind you of before we go on, since we're kind of at this place where it can sort of fit in, is sometimes AP wants you to write a general expression relating the rates of 2 reactions, or 2 reactants and products. So you'll notice that the way I've written this is the change in concentration of one chemical over time equals a change in concentration of another one over time. And we have to put a fraction here in front to represent the relationship between those changes. And so what we do is we always do 1 over, and then on bottom you put whatever the coefficient is. So this one would be 1 over 2, and this one would be 1 over 1. So you can see it says that, that the relative rates of each other have been set equal to each other. And so that's just how you write the general expression. Number 9. They're giving us the rate law for this reaction up here, and they are adding a mole of hydrogen gas and they want to know what's going to happen. If you're starting to think, well, we're adding hydrogen, it's going to shift to the right, that kind of thing, you're thinking more in terms of equilibrium. It's much simpler than that. If you add hydrogen to this, you're going to increase the concentration of hydrogen, and so you should speed up the reaction, right? Because you'll double this, and then it will get multiplied and increase the rate. Now, but they have this other thing going on here where they're talking about the rate constant. So you can see the rate of the reaction will increase, no doubt about it, but what will happen to the rate constant? And you can hear from the term constant that it implies that it can't change. So it is true that in this particular condition, the answer is the rate constant will not change. So I think B should be the correct answer. The rate of the reaction and the, oh no, not B. The rate of the reaction will increase, so it looks like C. Nope. The rate of the reaction will increase and the rate constant will not change. Yeah, D is the correct answer because the rate constant won't change. Now, I don't want you to think that nothing changes the rate constant. As a matter of fact, almost everything does. The only thing that you can change and not change the rate constant are these two concentrations. If you change those, the rate constant is still good. But if you change the temperature, the rate constant will change. So as long as you're changing concentration, the rate constant will be constant. So the answer is D.